Today we're looking at the multiplication of complex numbers. So we can multiply complex numbers either by a scalar, which is just a constant number, or we can multiply two complex numbers together. Algebraically, we use the same process of multiplication as usual. We just have to be careful when simplifying any i's. Just a quick note that when we multiply a complex number by a constant, this scales the distance geometrically of that complex number from the origin. If we multiply a complex number by I, this will rotate the complex number 90 degrees or pi on 2 radians anti-clockwise. First example, what is minus 2 times z if z is 2 plus 4i? To do this, we just multiply like usual. So we'll get minus 2 times 2 plus 4i. Minus 2 times 2 distribute like usual is minus 4. Minus 2 times positive 4i. Multiply the numbers together. That will be minus 8i. Let's sketch this on our complex plane. To sketch Z, recall that you go 2 units across on the real axis and then 4 units up the imaginary axis to this point here. To sketch minus 2 Z1, remember that's minus 4 minus 8i, so we go 4 units along in the negative real axis and then 8 units down on the imaginary axis. The first thing you should notice is that it's reflected Z1 over the origin, so it's in the opposite quadrant, and also the length of minus 2z1 is double the length of z1 from the origin. Why is this? Well, timesing by a negative reflects the point over the origin, and timesing by 2 doubles the length of the point from the origin. Let's use the same process to do part B. So firstly, we're trying to find 3 times z2, where z2 is 3 plus 3i. Again, distribute like normal. We'll get 3 times 3 is 9, and then 3 times 3i, well, that will just be 9i. Notice that this will triple the length of z2 from the origin, but it will be in the same direction as z2 because there's no negative there. Let's sketch both of these. Z2 will be 3 across and 3 up, and 3z2 will be 9 across and 9 up. I can't quite fit it in my axis, but we're going to get the idea. It will be somewhere a little bit higher up than this point. Notice they are in the same direction from the origin. 3z2 will be triple the length of z2 from the origin. Let's try and do I times z2. I'll have I times 3 plus 3i. When I distribute, I'll get 3i. Then I'll have I times 3i. So that will be 3. I times I is I squared. Just recall that I squared is negative 1 and replace that in there. So we'll get 3i minus 3 or minus 3 plus 3i to have the real part first. This will rotate z2 pi on 2 anti-clockwise around my plane. If I draw lines from IZ2 and Z2 to the origin, we can see that indeed I have rotated Z2 anti-clockwise around 90 degrees to find IZ2. Now we know how to multiply by a scalar. Let's see how you multiply two complex numbers together. Know that we know usually how to expand something like 1 plus 2x times 3 plus 4x. You might use the FOIL method to do that. Multiply the first components, the outside components, the inside components, and the last components together. And we should get something like 3 plus 6x plus 4x plus 8x squared. We can then combine the like terms in the middle here, and we'll get 3 plus 10x plus 8x squared. This process is exactly the same process as what we use for complex number. You just have to be a bit careful when multiplying the i's together. Let's try it for a plus ib times c minus ib, where a, b, and c are just constants. We'll have the a times c first. This will just be simplified as ac. I can next times the a times minus ib. That will be minus ab. I'm going to put the I at the end. Then we'll have c times ib. That will be cbi. And then I'll have ib times minus ib. Positive times a negative is a negative. B times b is b squared. And I times I is I squared. Notice that I squared will become negative 1 here. So that minus b squared I squared is actually part of the real component of my complex number. Let's group these together at the front. I'll have ac minus b squared times minus 1. And let's leave all the others with just an I at the back, and we'll deal with them in a bit. Because I have a minus 1 here, for my real part, I'll end up with ac plus b squared. And the imaginary part, let's take the I out as a common factor and a minus out. I'll get minus I times AB. Because I took a negative out, I'll get minus CB. AC plus B squared is my real part, and AB minus CB is the imaginary part of this complex number. Let's try it with actual numbers here. If I have the square root of 2 plus 3i times the square root of 2 minus I, again expand like usual. Root 2 times root 2 will just be 2. 3i times root 2, that will be 3 root 2i with the numbers in front of the I. Minus I times root 2, that's minus root 2i. And then 3i times minus I, that will be minus 3. I times I will be I squared. Again, group the 2 and the minus 3i squared together. Notice that I squared is minus 1, so we'll get 2 minus 3 times minus 1, plus take the i's as a common factor for the last two terms, 3 root 2 minus root 2i. Then we can say, well, 2 plus 3 plus 3 root 2 minus root 2, that will just give me 2 root 2i. Gives me the complex number 5 plus 2 root 2i. Lastly, we're going to find and sketch the complex conjugates of the following numbers. Excuse my graph, complex numbers. The conjugate just means you flip the middle sign from negative to positive or positive negative. So, for the first question, if we have 2 minus 5i, just flip the middle sign to its opposite. So the complex conjugate, denoted by a line above Z1 or whatever you're taking the conjugate of, is equal to 2 plus 5i. If I sketch Z1, I'll go 2 units across my reel and then down 5 units. The conjugate of this will be 2 units across, but now 5 units up. Notice these are just reflections over the x-axis. If I have Z2 equals 3i, I could rewrite this as 0 plus 3i, and the complex conjugate of Z2 would be 0 minus 3i. If I sketch this, Z2 will be 3 units along my imaginary axis in the positive direction, and the conjugate of Z2 would be negative 3 units, so down 3 units along the imaginary axis. Again, these are reflections of each other over the real or horizontal axis here. Lastly, if we have Z3 equals 2, I can write this as 2 plus 0i. Now it's easy to find the conjugate is 2 minus 0i. This is the same thing as just 2 because I have 0 parts for the imaginary part of my complex number. Actually, Z3 and its conjugate, 2 and 2, are actually the same number. Again, if we have a look at it, this is still the reflection over the real axis. This exercise is about 16A, 16B, and 16C questions.